Explain the trend in ion-ion forces as it relates to the sizes of the ions. Give one example of two ionic compounds and explain why one of them has stronger ion-ion forces. This one specifically says sizes of the ions, and let's take you through this process. So, and in fact, I think there's two questions in this, and so that's because there are two trends in ion-ion forces, one of which we've already talked about, but I'm going to go over it again. Deals with the product of charges, and the other one deals with, so if product of charges are equal, then look at sizes of ions. Colon, smaller ions have larger ion-ion forces. Okay? And product of charges, we've talked about an example of that. If we were to compare, and we'll do a different example this time, how about magnesium oxide and sodium chloride? Actually, we'll do sodium fluoride. And for these, if we look at the product of charges, magnesium's 2 plus, oxide is 2 minus. That's going to be a -4. Here we have +1, -1. That's just -1. So we would say that magnesium oxide has two things. One is it has the larger ion-ion forces. It's also true, though it's not necessarily part of this class, that MgO has 4 times the ion-ion forces of sodium fluoride, and that's all related to Coulomb's law from physics class, because you're basically treating these as charges that attract each other. And again, we don't have to know that for this course, but it is true that it's 4 times greater because the product of charges is 4 times greater.
Professor?
Yeah, Daryl?
Is that not supposed to be magnesium dioxide?
It is not supposed to be magnesium dioxide. It is, you mean the name of it or the formula?
The formula.
Yeah, so the magnesium oxide, so since it's +2, -2, these balance exactly. So MgO is the correct formula.
Yeah, but how come it's -4?
Oh, so the product of charges, product means multiply, which I know you know, but yeah, no, it's yeah. So yeah, I know you know that, but it's a new sort of place to see it. So this is just +2 times -2. Yeah, I think you get it.
That makes sense.
Yeah. No, and so I don't know. If you've had physics, I mean, I think again, I'm not a physicist, but if you look at Coulomb's law in terms of energy and not force, it's 1/4 pi E naught maybe Q1 times Q2 over R, I believe. Anyway, it could be R squared. I never remember that. I think the force is R squared, but it's these two are the charges. So you'll see if you've had physics, then you might have seen this. If you haven't had it already, then you'll see it coming up. But that's where this idea comes from. Now, but let's suppose you have sodium fluoride versus sodium chloride. And now these, so if we look at the product of charges, and we always look at the product of charges first, the product of charges is the bigger trend, is the easier trend, is the bigger trend, is the trend with the larger magnitude. So this is going to be +1, -1, +1, -1. So our product of charges are the same. So then we look at ion size. And this comes back to our trends in ions and the periodic table, which is around here somewhere. There we go. So my question for you, well, the sodium is the same, so we don't have to worry about that. But fluorine or chlorine, just talking about the atoms, which one is smaller? Fluorine atom or chlorine atom? Do you remember?
Fluorine is smaller.
Thank you, Daryl. Very good. Fluorine is smaller. And if you remember our trend in atom size, we said that as you go from the n equals 2 to the n equals 3 to the n equals 4, the atom gets bigger. Well, since these are F minus and Cl minus, they're both the -1 charged ions, the trend still holds. And we did talk about that too, though not as much. So fluoride, F minus, is smaller than chloride, Cl minus. Fluoride is smaller than chloride, just like fluorine is smaller than chlorine. And sodium fluoride, because it's smaller, has the larger ion-ion forces. So I guess I'll just write it the other way. Sodium fluoride has larger ion-ion forces. Because fluoride, F minus, is smaller than chloride. All right, and I think that's pretty much the last trend in intermolecular forces that we have to deal with. I think, yes. So we do have one other question to do, but as you've seen, 90% of the homework, 90+% of the homework deals with intermolecular forces. So you can bet that when we get to the final exam, you're going to have a lot from this chapter on intermolecular forces. And I would guess that I will pretty much just copy and paste those two 10-part questions onto your third exam. And for those of you keeping score at home, so the third exam will be about the material since the second exam. It will be the last week of class before, and it will be before finals week, and then we'll have a cumulative final. Any questions about, oh, so did I answer the question? Always good to check in there. Explain the trend in ion-ion forces as it relates to the sizes of the ions. It looks like I sort of did here. Yeah, I think I did. I guess technically I should say larger product of charges equals larger ion-ion forces. Like that statement would really do well for number 1 if I was about product of charges, but since it's about sizes of ions, I think this is a pretty good answer. It gives a pretty good example too.